Can you hear me?
Yes.
40 years ago I wrote a paper, Breakdown of Predictability in Gravitational Collapse, in which I claimed there would be loss of predictability of the final state if the black hole evaporated completely. This was because one could not measure the quantum state of what fell into the black hole. The loss of information would have meant the outgoing radiation is in a mixed state, and the S matrix was non-unitary. The paper was very controversial. It was rejected by the Physical Review, and accepted only after much argument, and a delay of a year. Since the publication of the paper, the ADS-CFT correspondence has shown there is no information loss. This is the information paradox. How does the information of the quantum state of the infalling particles reemerge in the outgoing radiation? This has been an outstanding problem in theoretical physics for the last 40 years. Despite a large number of papers, see the AMPS firewall paper for a list, no satisfactory resolution has been advanced. I propose that the information is stored, not in the interior of the black hole as one might expect, but on its boundary, the event horizon, in the form of supertranslations of the horizon. This is a form of holography, recording the state of a four-dimensional region on its boundary, the horizon. The concept of supertranslations was introduced in 1962 by Bondi, Metzner, and Sachs, BMS, to describe the asymptotic group of asymptotically flat space in the presence of gravitational radiation. The BMS group is a semi-direct product of the Lorentz group, with supertranslations. A supertranslation alpha moves each point of future null infinity, a distance alpha to the future, along the null geodesic generators of future null infinity stripe plus, while keeping theta and phi on the two-sphere unchanged. In other words, the retarded time u is replaced by u prime equals u plus alpha. The usual time and space translations form a four-parameter subgroup of the infinite-dimensional supertranslations, but they are not an invariant subgroup of the BMS group. Listening to a lecture by Strominger on the BMS group at the Texas in England workshop this April, I realized that stationary black hole horizons also have supertranslations. In this case, the advanced time v is shifted by alpha. V prime equals v plus alpha. I discussed my idea with Malcolm Perry and Andrew Strominger. The null geodesic generators of the horizon need not have a common past endpoint, and there is no canonical cross-section of the horizon. I take the tangent vector L to be the horizon to be normalized, to agree with the killing vector. time translation plus rotation, on the horizon. Classically, a black hole is independent of its past history. I shall assume this is also true in the quantum domain. How then can a black hole emit the information about the particles that fell in? The answer, I propose, is that the information is stored in a supertranslation of the horizon that the ingoing particles caused. In his recent paper, Chaos in the Black Hole S-Matrix, Polchinski has used a shock-wave approximation to calculate the shift on a generator of the horizon, caused by an ingoing wave packet. Even though the calculation may need corrections, this shows in principle that the ingoing particles determine a supertranslation of the horizon. This in turn will determine varying delays in the emission of wave packets along each null geodesic generator. The information about ingoing particles is returned, but in a chaotic and useless form. This resolves the information paradox. For all practical purposes, the information is lost.